So picking up on our final lecture of the chapter 30 about sources of the magnetic field, we're going to start out by talking about the magnetic moment of atoms. So if we think of an electron circling an atom in the simplest cartoonish way, we would think about an electron going in a circular path around the center of our atom. Right? And so our magnetic moment, if we try to describe our current in terms of that electron going in a circle, we would say that an electron goes by every period of motion. So that electron has charge E, right? The 1.6 times 10 to the minus 19 coulombs, and it would have a negative charge, but current is described as the direction of positive charge's motion, so we can get rid of that negative. It is going at a certain velocity, and it is going around a circle that we're going to describe as being 2 pi r in circumference. So that is a charge going around every certain amount of time. Now we're going to use a couple definitions. We're going to define a dipole moment being I times A, and we're going to define the area of this dipole moment as the area of the circle that this electron is cruising around. So our dipole moment, if we substitute in EV over 2 pi r as our current, which isn't necessarily a steady current, but we'll say our electron's going fast enough that it's close enough, and A as being 2 pi r, we can see we can cancel some stuff out. And we get a magnetic moment, or a dipole moment, that looks like 1/2 EVR. Then we can define an orbital angular momentum. So orbital angular momentum. So angular momentum is just one of those circular motion things that you should have learned last semester. So orbital angular momentum, we've got L as our descriptor, or as our usual letter that we use for angular momentum. Our mass of our electron, so we'll give it a little subscript E, moving at a certain velocity out at a certain radius. So that's an orbital angular momentum. And we can describe our dipole moment, or our magnetic moment, as mu, our charge of our electron, over 2me times this orbital angular momentum. So we can describe our dipole moment in terms of our orbital angular momentum of our electron. Now, in actuality, quantum physics tells us that this is too simple of a description of our electron moving in a circle, right? And that we also need to take into account the spin of an electron. So the spin for an electron happens to be the square root of 3 over 2 times h bar, where h bar is a constant that we use in quantum mechanics. And quantum tells us that the orbital or the magnetic moment of our atom is actually going to be something of the order of the square root of 2 times E over 2me times h bar. So it's a little more complex than this simple case. And that is going to get us to something called the Bohr magneton. So the Bohr magneton, we usually use a subscript B with that mu for the Bohr magneton, and it is E times h bar, which is just Planck's constant divided by 2 pi. So it's just a number, divided by 2 times the mass of our electron. Right? And the Bohr magneton, since these are all constants for an electron, is 9.27 times 10 to the negative 24th, and that is in joules per Tesla. So that's a really quick, brief explanation of the magnetic moment of atoms. What that is going to get us to is talking about magnetic materials and why some things are magnetic. When we describe magnetic materials, we can describe 3 different types of materials, really. We can describe things that are ferromagnetic. So these are the things you usually think of as magnets. We can describe things that are paramagnetic. And we can describe things that are diamagnetic. So when you describe something that is ferromagnetic, those are metals and materials like iron, that's where the ferro comes in, like iron that can be made into strong magnets. So these are items that can become permanent magnets, are your ferromagnetic materials. When you have ferromagnetic materials, you have a high degree of alignment of the magnetic dipoles of your atoms or your molecules in your ferromagnetic material, even when you've got weak external fields. So they'll align even with weak external fields. Now, when you have something that is paramagnetic, you get a partial alignment of your electron spins in metals. The atomic and the molecular magnetic moments partially align as well when you apply a magnetic field, and they partially align in the same direction of the field. So if we want to picture these 2 items, you apply an external field to your ferromagnetic material, and your ferromagnetic material is going to align its dipole moments in the same direction. Even later, those dipole moments will remain aligned in that same direction. For a paramagnetic material, if you apply an external field, your dipole moments are going to be weakly aligned in that same direction. So it means some, but not all. You've got a weak alignment. And later, if you take away that external field, the paramagnetic material will be easily randomized. Now, a diamagnetic material is slightly different. Think of the word diapose, right? So when something's diamagnetic, the orbital magnetic dipole moments will actually induce themselves in the opposite direction. They'll oppose an external magnetic field. This is definitely observed in materials whose atoms have no permanent magnetic moments, and it can happen in all materials. So you apply an external magnetic field, and if you have a diamagnetic thing, it is going to be weakly aligned in the opposite direction. And again, if you take away that external field, you're going to have a random alignment later. So ferromagnetic are the most common you think of when you think of magnetic materials, but you can get other non-magnetic materials to have some magnetic behavior and have some alignment. So when you talk about magnetization and susceptibility, when you talk about something being magnetized, you can describe it by how the dipole moments are lined up per unit volume. So if something's very magnetized, you've got a lot of lined up magnetic dipole moments per unit volume. Now, when you drop or hit a magnet, you can demagnetize. So if you were to take a hammer to a permanent magnet or just dropping a permanent magnet, you can cause a disruption of those alignment and you can lose some magnetization. The other way you can demagnetize something is by heating it. So heating something allows atoms and molecules to rearrange themselves, and heating a permanent magnet can cause a loss of magnetism. So there is a temperature where we know this happens. So Curie, as in Marie Curie, there's a Curie temperature where above this a magnet cannot be made. So this is a specific temperature. It's almost like a melting point, but it's not a melting point. It's like the melting point of magnetization, right? It's not a physical melting point. So the Curie temperature lets us know that above this temperature, a magnet cannot be made. So for iron, that temperature is pretty high. It's not above its melting temperature physically, but it is 1043 Kelvin for iron. Other materials, it's even lower. So what does this tell you? This tells you that if you're gonna engineer something for application in a high temperature thing, you don't only have to worry about, whether this item's gonna melt, but you're gonna have to worry about whether the magnetic field or the permanent magnetization of this item is gonna change. So it's believed that all magnetic fields are caused by electric currents, and the electric currents in our permanent magnet just happen to be at the atomic scale. I've linked some minute physics videos to help you guys with that, but my own version of that is some materials engineering stuff that I love. So magnetic materials, when you have a material that has polycrystalline structure, which most metals do, you can have random alignment of the atomic magnetic dipoles. So that's what this image is showing. It's showing random alignment with these red arrows. Now, when you apply an external field B, you more or less influence those atomic dipole moments to align in the direction of that B, right? So it's like a current loop and the torque on a current loop in an external field, right? So the torque on these magnetic dipoles, because of that external field, causes them to start aligning. Now, when you have a ferromagnetic material, these can begin to align and then stay aligned even after you take away the external field. So as the field is made even stronger, you can have the domains with magnetic moment vectors not aligned with the external field becoming very small. So what this is called in crystalline structures is Oswald ripening, where the domains that are majority domains start growing and taking over regions of this minority domain. So our magnetism and matter, remember we have ferromagnetism, paramagnetism, and diamagnetism. We can talk about the susceptibility and the saturation. Saturation is when most domains are aligned. And we can talk about the relative permeability of our magnetism and the regular magnetic susceptibility. So review that in your textbook, but this is the end of chapter 30, and we'll start with chapter 31 next time.